Have you ever wondered how a tiny sparrow, weighing less than 30 grams, manages to overcome gravity and take to the sky? Meanwhile, humans, with all our modern technology, need an engine weighing tons just to achieve something similar. Sounds absurd already, doesn't it? But here's a detail that will leave you even more astonished. An eagle's bones, though far lighter than human bones, weigh only half as much as its feathers. Just imagine that. A creature whose outer coat is heavier than its own skeleton, and yet it still soars into the sky, with some species flying non-stop for thousands of kilometers without resting, without landing, without stopping to refuel. And here's the detail that has puzzled scientists for centuries. The flight-adapted structure of a bird's body is so close to perfect that humans, despite inventing airplanes, helicopters, and even drones, have never managed to replicate it exactly. So what exactly turned these small creatures into the most perfect living flying machines on the planet? Let's spend the next 12 minutes figuring it out together. Picture this. Every day you have to go to work. But instead of riding a motorbike or driving a car, you have to burn your own body's energy just to fly there, sometimes over a distance of several hundred kilometers. Just thinking about it sounds exhausting, doesn't it? Yet that is the completely ordinary daily life of a migratory bird. If we had to compare the two, the human body is like a bulky, heavy cargo truck. A bird's body, on the other hand, is like a Formula One race car, designed to be minimal down to the last centimeter. Anything excessive gets stripped away without mercy. Believe it or not, most bird species don't even have a bladder to store urine. Why? Because to them, even one overweight organ is enough to slow down an entire long flight. So instead, they simply expel waste immediately rather than storing it the way we mammals do. Not only that, many bird species don't have a single tooth. At first glance, this might seem like a major disadvantage, but it's actually an incredibly clever weight-saving strategy. Think about it. A jaw full of teeth along with chewing muscles would weigh far more than a hollow, horn-like beak. So instead of chewing, birds swallow their food whole, then rely on a special organ deep within their digestive system, called the gizzard, to grind the food in place of teeth. In short, the ancestors of birds went through the most brutal downsizing in evolutionary history, where any organ that didn't directly serve the purpose of flight was eliminated or shrunk to the bare minimum. Now let's talk about the skeletal framework, the foundation of this entire living flying machine. In the scientific world, this is called pneumatic bone. But to picture it more easily, imagine it like a hollow sponge. Instead of being dense like human bone, it's hollow and filled with air pockets, not unlike the structure of lightweight foam bricks used in modern construction. Interestingly, despite being hollow, these bones remain remarkably strong, thanks to tiny internal struts crisscrossing inside them, following the very same principle engineers use when designing steel bridges or aircraft frames. The entire skeleton of a pigeon, including the skull, accounts for only about 5% of its body weight, far lighter than the 15 to 20% found in humans. Yet that fragile-looking skeleton can still withstand the enormous forces generated every time the wings flap dozens of times per second. Then there are the feathers. Instead of using the dry scientific term branching keratin structure, we could playfully call this a lightning bolt armor. Why? Because each feather is made up of thousands of tiny barbs that hook together just like Velcro, creating a surface that is lightweight, sturdy, and remarkably effective at cutting through wind. Even more remarkably, if a barb happens to separate due to strong wind, the bird only needs to preen it gently with its beak, and those tiny hooks automatically lock back into place, restoring the feather's surface to perfection as if nothing had happened. It's no exaggeration to say this is a self-repairing technology that even human-invented Velcro could learn from. And the part considered the true heart of flight is the chest muscle, known as the pectoralis. You can picture this as a pair of powerful twin engines, since this muscle mass makes up 15 to 25% of a bird's body weight, many times greater than the roughly 1% ratio found in humans. It's this massive muscle that generates enough force with each wing beat to lift the bird's entire body off the ground and sustain it throughout a long journey. But wait, here's the most illogical part of the whole story. If hollow bones combined with powerful chest muscles were the formula for flight, then why can't the ostrich fly, a bird with nearly solid bones, far heavier than those of other birds, and certainly no lighter at all? And the paradox goes even further. Penguins possess nearly perfect skeletal and muscular structures for flight, with extremely powerful chest muscles and relatively light bones. And yet, they can't lift off the ground at all, waddling around clumsily and almost comically whenever they walk on ice. If flight were simply a matter of light bones plus strong muscles, then why do these two birds completely defy that rule? At this point, many of you are probably pausing to think this through. The answer lies in an important truth that very few people notice. Flight isn't simply about being light or strong. It's the perfect coordination of 4 factors at once: wind shape, the muscle-to-bone ratio, a specialized respiratory system, and, most importantly, the evolutionary pressure that each species' environment placed upon it. Ostriches, despite having bones as dense as a human's, had ancestors who chose a completely different evolutionary path. Instead of investing everything into their wings, they poured all their resources into long, powerful legs, allowing them to run at speeds up to 70 kilometers per hour, faster than most predators on the African plains. For ostriches, running away is far more effective than flying, simply because their habitat consists of open grasslands with no trees to fly up and hide in. And so, over millions of years, their wings gradually degenerated, retaining only a role in balance while running, and occasionally in mating displays. Penguins, on the other hand, took a completely opposite path. They kept relatively light bones and extremely powerful chest muscles, but completely repurposed their wings. Instead of flapping through thin air, they used those very same wings to fly through water, a medium nearly 800 times denser than air. That's why, when swimming, emperor penguins can reach speeds of up to 35 kilometers per hour underwater, rivaling the flight speeds of many airborne birds. Their bones are also slightly denser than those of flying birds, reducing buoyancy and making it easier for them to dive deep. This is truly an intelligent trade-off between the ability to fly and the ability to swim. And the greatest secret? The thing that truly gives birds their extraordinary flying ability beyond any other creature lies in their lungs. Human lungs work in a simple in and out cycle, which means some stale air always gets trapped inside and never fully escapes. But a bird's respiratory system works completely differently. They have an additional network of air sacs spread throughout their bodies, even extending into those hollow bones we mentioned earlier. This system allows air to flow continuously in one direction through the lungs, meaning birds always receive a fresh supply of oxygen on both the inhale and the exhale, with no stale air ever wastefully trapped inside. This is the supercharged engine that gives birds enough energy to sustain flight for hours on end, even thousands of kilometers without rest, like the bar-tailed godwit, a species capable of flying non-stop for nearly 11,000 kilometers from Alaska all the way to New Zealand, without ever stopping to eat or rest for even a moment. This is something no machine humans have ever built has managed to achieve with the same level of energy efficiency. So, flight isn't some simple formula of light bones plus strong muscles. It's the result of tens of millions of years of evolution, where every single detail of a bird's body, from its hollow bones, self-repairing feathers, and massive chest muscles, to its remarkable one-way respiratory system, has been fine-tuned to perfection, all in service of a single purpose: conquering the sky in the most efficient way nature has ever devised. And perhaps that's exactly why, despite how far science and technology have advanced, humans still haven't been able to build a machine that flies as efficiently and elegantly as a real bird.